All right. Good afternoon, Lynette and Jehan. And I guess Christian said he will not be able to join us today, but there's still a handful of your classmates who are not yet here. I'll be recording anyway, so I would like to start early so that we can try to finish everything today, and then I'll draft a sort of a short description of the project, and I can email it to you guys. And if you have some questions, then I can meet you, or no, I'll be waiting on Tuesday. I'll open this Zoom meeting. You can attend if you have some questions. If you don't have any questions, you don't need to attend. You can just go ahead and start the project. But the assumption there is that I finished discussing everything today, right? Because essentially your project will be about clustering and classification algorithms. In a nutshell, I want you to pick your own data, try to find a data set, or you can do measurements, or you can search the net, what are the available data there, or look at your particular something that pique your interest. Pick of a particular topic, say you want to say what would be a nice topic. Say you want to know which stock to invest on. So you can download the data for say the stock prices for the last say 30 days. So you have the stock prices in the last 30 days, and then you can also download some recommendations from say some from Investopedia or from some other open source financial websites. They rate stocks say if if they have a buy rate, so meaning they suggest that you buy it, a sell rate, or a sell or a hold. So those are the three possible classification of stock. So, and then you can select as training data, say get the rating for 50 of the stock. So you will train a machine learning algorithm, either a classification or a clustering algorithm, or not clustering, but a classification algorithm based on those 50 stocks. So you will input in MATLAB, say the closing price for the stock, and then you will give it the key, which tells MATLAB what's the recommendation for that stock. Should you buy, should you sell, or should you hold? All right. Now and then based on the statistics that you have downloaded, you can input, say, for Jollibee, which is not part of your training data. You can ask your machine learning algorithm to classify Jollibee, whether it should be bought, sold, or it should be held, right? Depending on the price, which you also tried to which you also tried to which you used, or the predictors that you use to train your data set. So really, I want you to create the things I'm doing right now with the Irish data set, but on your own data set. So you have the freedom, and then you will just run probably a couple of the algorithms that we discussed or we will be discussing, and then you put it in a nice report, and then draw up your own recommendations based on the data that you get. All right. So, but I'll give you more details on a written form, probably by Monday, but I'll try to do it over the weekend because my promise is that I'll complete the uploading of the videos and the materials by Friday, by tomorrow. So that's what I'm gonna do all day, except when I'm holding classes. If I forget by tomorrow end of day, then you can spam me with emails and personal messages so that I get pressured to finish it, right? So that over the weekend everything should be fine. You can go over them, and on Monday you will get the instructions for the last problem set, and then you can start doing it on Monday. Then if you have questions, I can meet you on Tuesday, and we can clarify things out. Okay? So I hope that's a good plan. Now, I think last time I just presented the MATLAB code for which algorithm that is, for hierarchical clustering. Now let me present the last two, but probably quickly because the codes are not that very difficult. Now I hope you can see my MATLAB screen, but I think I won't see your reactions now, but You can put it in the chat if you can see it. I hope you can, and the font is not.
Yes, sir.
All right, thank you. So this is the code that we have for hierarchical clustering. Okay, so I hope this is straightforward. I will also upload the snippets of codes so that you can just play with it, or if you want, you can modify it accordingly. Okay. Now, probably let's start with the DB scan. Remember, in DB scan, you need two particular parameters. You need the density and the radius. And essentially, you're counting how many neighbors within epsilon units are there with the for every set or for every point in the data set. And if it will pass the density threshold, so if the number of neighbors within epsilon units is greater than the set density, then your point will be a 4 point, right? Otherwise, it will be a border point. It will belong to the neighborhood of a 4 point, and elsewhere it is an outlier. And then the clustering will be will be decided upon the accumulation within core points. So if core points shared a same boundary point, then they will be in the same cluster, right? So let's see how I implemented it in MATLAB. Actually, it's just a couple of lines. So first, line number one, I will load the data from MATLAB, the Fisher-Irish data, which again contains four measurements: petal width, petal length, sepal width, and sepal length. And I still forgot to check the documentation if what's exactly are the columns there. But let me see if I can do that here. Let me open Fisher Irish. Okay. Oh, I'll search for documentation. But anyway, maybe in MATLAB search later I can find that. So you will load Fisher Irish here, and then you can decide what is the epsilon, what is the radius that you want. So basically, the columns. So if I load Fisher Irish, you already know that this contains two things. Number one, if you see on my workspace on the left, you see here there's a matrix mesh. So 150 specimen with four measurements each. So you can think of our data to be vectors of four entries or four components. So it's sepal width, sepal length, petal width, and sepal length in a certain order. I just forgot to order it. Now, you can decide now what is the epsilon. So um how big should be the neighborhoods, right? So we don't want the neighborhoods to be very small, because if the neighborhoods will be very small, that means your epsilon is really very small. Then there's a lesser chance that there is another data point within that epsilon neighborhood. So we want epsilon to be a little large, but not too large, because if it's too large, then everything will be a core point, right? So there would be no outliers or border points. So you can try to supply this parameter via trial and error. Or I found a nice way to do it. There's a MATLAB command, and that's the cluster dbscan that estimate epsilon command, which will compute the best epsilon according to some heuristics. I'm not sure what exactly the heuristics is, because I just downloaded it from the radar toolbox. You cannot use this command, line number 8, if you don't have the radar toolbox installed. So if you haven't installed it, then you need to play with line number 3, right? So you need to supply your own epsilon. But since I have the radar toolbox, I can use this command. I will just put as input the matrix. Now I am training my algorithm using all the columns of the matrix mesh. So I'm using all four measurements as my training data set. That's why I mentioned our data set. Our data set is composed of four vectors, right? Vectors, 150 vectors of four components. And then K is a parameter. This is basically the estimate epsilon command that I am using here uses the KNN algorithm. But we haven't talked about the KNN algorithm. You will know it later, but you need to select the value of K. the number of neighbors, because what it will do is that it will count the neighbors, the nearest neighbors of uh, the k nearest neighbors of a certain point, or each of the points. And then it will compute what's the average distance of those 8 nearest neighbors to the point you are considering. So here by default, I'm using 8 to 30. So it will run KNN iteratively by using 8 neighbors up to 30 neighbors, and it will choose the optimum epsilon. All right. But again, if you don't have the radar toolbox, then you just need to supply your own epsilon. Okay. And then I am using theta, which is the density. Now, theta is another parameter that you can set, but I read somewhere last semester that it is twice the number of columns of or the number of measurements, right? So hold on, size. Let me see size. Let me double check that. Help on size. Yeah, it is the number of columns. So in this particular case, I automated the computation of the number of columns. So you can do so by invoking the command size. If you just type on the command window size of your matrix mass, it will give you all the dimensions, 150 by 4. But if you want to get the second component, the second size, to tell you how many columns there are, so you need to type size of measurement. So you want to count the number or the dimension of size, but the column. You put 1 for row, you put 2 for column. So that means this guy will give me 4. Oops, sorry. It will give me 4. And as I mentioned, I read somewhere that one nice guess for theta would be twice the number of columns. So that's why I chose theta to be twice the number of columns. So that's going to be 8. But you can select your own theta. You can supply theta, but we are not sure if that would be the optimal one. But after all, data science is a hit or miss method, right? It's a trial and error thing. So you can play with these two parameters. And then after that, all the heavy works are done, because all you need to do is to invoke the one-liner command dbscan. All right. So I am just putting the answer in the vector species, but probably I should put it as species list, because species was already used here, which is the key to correction, sort of, in the uh in the um in the Irish data set. So the Fisher Irish data set, it has the answer key, right? Sort of what is the actual variety of each of the specimen in the rows. But probably so that our algorithm will be blind to that, maybe I should delete species from the workspace, but I am not invoking it anywhere. So here I am putting inside the vector species list the result from dbscan, right? The command for dbscan is simply dbscan of the following inputs. The first input is the matrix of data that you have, right? Sorry, by default, the rows, sorry, hold on, guys. The default is the specimen would be the rows and the measurements will be the columns. So that's how you feed your data. So make sure that the rows correspond to each point in your data set and the columns are the predictors or the data for each of the specimen in the data set. Okay. The next input would be epsilon, the radius of each of the neighborhoods you want to use. And then theta is just the density threshold. And then there are various name value arguments or name value argument pairs that you can choose from. Say here, I'll just tell MATLAB what kind of distance I want to use. Maybe I want to use the Euclidean distance first. So I can put that there. And then to see our results, to visualize our results, I'll just create another G scatter plot, right? So a colored scatter plot. So here, because the scatter plot is only two-dimensional, I will just plot the species list for each of the data point in terms of the third column of the measurement matrix and the fourth column. So the third column of the measurement matrix will be the x components in the scatter plot. The fourth column will be the y axis, right? And then the species list will determine the color. Of course, I used here the entire matrix mesh. So you could have drawn the scatter plot in terms of the first and the second column, the second or the third column, etc. But I guess to keep it similar to what we had with the hierarchical search, so I'm just using the third and the fourth columns. All right. So any questions about this code? Right. I'm guessing there are none. Of course, you won't have any questions because number one, this is a very simple code. And in general, even if it's a simple code, you cannot see a question because it is presented very simply, right? But once you try running it, you might run into problems. And that's where we can use the other classes after next week, right? So you can still consult, especially when you're doing the homework and the codes that I supply to you are not working. So you can set an appointment with me. I'll keep my 5:30 to 7 free for Tuesdays and Thursdays. All right. Now let's see. Let's run this. I'll hit F5 on my keyboard. Then we'll see the results here. Okay, it's running. And then here you see the results of the results of the scatter plot, right? So here, since our machine learning algorithm is blind on the actual species list, it's just knew that those specimen that has third measurement and has fourth measurement within this data points, then they are grouped together. Meanwhile, you see here that all the yellows are grouped together. And for some reason, this and this guys are joined together. All right. Or actually, no, they are not joined together. They are considered to be outliers because the label is -1. Right. So with the Euclidean distance, DBScan only predicted that there are two classes, and it treated or the 4 points, the four blue points, to be outliers because they are not a core point and they are not within the boundary of a core point, within the neighborhood of a core point. Okay, but it will be interesting to see if what's the answer key. But I deleted the species list. Maybe I should reload the species list and let's see what's the actual answer, right? So that we'll have an idea of what's going on. So maybe here I can copy this and then create a scatter plot. But now this is species. This is the correct grouping, species. Then let me put a title here. So title, I'll put, this is the correct clustering. So that we know what we are expecting to get. So this is a luxury for us because we know the actual clustering. In real life, you might not have any access to the actual clustering, right? So it's just for verification purposes. This is the answer key, right? So this is what we should get. So you have the Setosa variant here in the lower left portion. And then somewhere in the middle, the red dots, they belong to the versicolor variant, and the yellow ones are in the Virginica variant. But look at what we got from DBScan. Here's what we got from DBScan. Right? Oops, there you go. So it treated most of the data points within this area to be of the same cluster, right? And it really makes sense that it will do that because you see that they are the data points are very close to each other. At least their third and fourth columns are very close to each other. So the machine learning algorithm, without any other knowledge, cannot distinguish the versicolor and the virginica variants from each other. All right. Now, what are the options that we can do, or what are the things we can do in order to try to improve our results? Well, maybe we can run, let me just put a close all here so that all the figures will be gone, right? Close all will just close all the open figures. So maybe we can try customizing the DB scan algorithm by choosing, say, a different kind of distance. Say we want, well, the nice thing about MATLAB, or this version, right? After you put distance, it will have a drop-down menu of all the possible distances that you can use. Say, let's use the Chebyshev distance, and then I'll press F5, and here, this is the correct clustering, and this is what we got. The left graph is what we got from DBScan. And there are no outliers now with respect to the Chebyshev nodes. The Chebyshev distance, because they are classified on either as group 1 or group 2. But there's still a problem here because it wasn't able to distinguish between versicolor and the virginica variant. But the Setosa variant seems very distinct insofar as the third and the fourth columns are concerned, so they are classified correctly. Okay. Now, but remember that our algorithm has access to all the measurements. So it seems that the problem is not just with with the third and the fourth measurements, but also the first and the second. All right. Now you can play. What are the other distances we can use? Probably you can try to use the, say, cosine distance. But this is quite different because the cosine distance is the angular distance, right? I explained its main difference to the other types of measurements last time. So here's the correct clustering, and here's what we got, right? So the cosine distance didn't do well because it treated everything to be of the same variant. And it makes sense because, again, the cosine distance measures the angle between the vectors, right? So if you have this point and this point, sorry, if you consider the following points, this point and this point, the Euclidean distance between them is quite long, right? Because the Euclidean distance between them is the length of the straight line. But the cosine distance between them is basically determined by 1 minus the cosine of the angle between them. So this is the angle between them, which is relatively small. So that's your theta. You get the cosine, and then you subtract it from 1. This would be the distance of those 2 points, right? So it's very small. And actually, probably if I use the cosine distance, I also need to adjust the epsilon because you're doing everything with respect to the cosine distance. So probably here we can just comment line number 9 because that's an automated thing. Maybe here we can say that the distance should be between should just be 0.5. Then let's try if we get some improvements. So here's the correct one. Oh, it seems there are still no improvements. There's still just one classification or clustering here. Perhaps perhaps the cosine distance is not a good choice. What are the other distances that we have? There's other distances here that we didn't discuss, so you can just play with them. Anyway, you can see what they mean by looking at the documentation page. So let's try. Correct. Oh, the city block distance or the taxi cab distance, we're able to predict. Actually, it didn't predict 3 clusters, but it predicted 2 clusters, the red ones, and the yellow ones, and all the blue ones are outliers. which is not a good thing. So the city block distance is not appropriate for our data here, right? So here we are experiencing, or we are seeing some of the disadvantages, or some of the those points where this algorithm is lacking, right? So if you want to take a look at the other details for the algorithm, you can just always right click on the command, click help on dbscan, and then it will give you the help browser. Then it will give you all the information about that command, right? And then all the different there are some help some examples here, and then it will give you all the possible options that you can put into it. So here you have your distances. So here are the options that you have, okay? And a short description about them. And then it will also give you some other arguments, okay? So that's the DB scan algorithms. Do you have any questions, guys? Okay, none? Let me see. All right. So now I'll go to the last clustering algorithm we discussed, the k-means algorithm. Well, the k-means algorithm, it actually computes. It starts with k, so you need to initialize the value of k, which is basically the number of clusters you are expecting, and then the algorithm will randomly select k centroids from your data set. It will compute and then it will compute the distance of each point from the centroids, and it will select which is the closest centroid. The closest centroid will be the cluster to which any data point will belong, right? So that's how the algorithm go. And then after the initial clusterings were done, you will again take the average per clusters, and then you will get the three new centroids, or k new centroids. And then after the k new centroids were obtained, then you will again repeat the algorithm of computing the distance of each point from all of the other centroids, and then you're going to choose which is the closest centroid. The closest centroid would be the cluster of the closest centroid will be the same cluster to which your data point will belong to. All right. Now let's see how it is implemented here. And actually, it's just a 16-liner code, and then I just put some modifications here. So again, line number one will just load the Fisher Irish data set. And then I specifically chose to just use the third and the fourth columns for this experiment. But again, you can keep the entire matrix mesh as your information, your information or your data for the training. Okay. And then what did I do here? Okay. In lines 5 to 9, I plotted the entries for or the data. So X components would be your petal lengths. That's the third column in the matrix mesh. The fourth column in the matrix mesh, which is the second column in the matrix X, will be the petal width. Just to see how they look like. So let me run lines 1 to 9. I'll hit F9. So we get this. Okay. So here are the data that we have. So petal lengths is in the x-axis, petal widths are in the y-axis, but we don't know what the variants are, because the algorithm should be blind from the correct clustering, right? But let's put it there just to visualize the data. And then the k-means algorithm is implemented in line 11. So the command is k-means, and the inputs are your training data. So for us, that's the matrix X. And then the next argument would be the number of clusters that you're expecting. All right. So here I'm expecting 3 clusters. So maybe to make it better, I'll put K here. And then, oops, what happened? Okay, I'll put K there, and then I'll just say K above. So you need to declare K above, say K equals 3. And then here are just some options. I displayed each of the iterations just to see how the algorithm is progressing. But you can delete this name pair or this name value pair, display an iter. And then in this particular case, I chose the distance to be squared Euclidean, right? And then here, lines 14 to 17 will again create the scatter plot. Now, the difference between k-means, dbscan, and and 3, k-means guarantees you that you will have k clusters, and k is a parameter that you feed into the algorithm. So you input k, then you will be sure that you will have k clusters, right? So let's run this. I'll press F5. And then you see here in the command window, here are it took 5 iterations for the for the um, for the k-means algorithm to converge, and the best total sum of distances is 31.37. But we don't need to worry about that number. What I'm after is figure number 5, which is basically the classification. Um, Based on petal width and petal width and petal length, right? Then let's compare it. One striking thing about this is we get exactly 3 clusters, and it seems that it was able to sort of differentiate the versicolor and the virginica variants. Now let's compare it with the correct clustering, and it seems it did a very decent job, right? So you have Setosa, which is, I think, 100% predicted well, right? But here you will have some problems with versicolor. Versicolor here would be these points, while the actual versicolors are these, right? It's a little bit different, but it did a good job, right? So knowing that they are not privy to other information other than the petal width and petal length. Okay. Now, again, as the other algorithms, you can play with the parameters that can be fed into this algorithm. So instead of, say, Euclidean distance, I can just choose, say, cosine distance. Let's see what will it give us. If you use the cosine distance, it will only took 2 iterations, and this would be the result that you get. Again, we were able to get exactly 3 clusters, but it's not a good classification. But the grouping, I hope, makes sense because here the angle between the blue ones are very small. The angles between the yellow ones are quite small, and the angles between the red ones are very small. So remember, cosine distance is all about the angular distance, right? But it seems that it's not appropriate for our data, so do not use the cosine distance there. Maybe we can try the Hamming distance. Let's see what it will give us. Yeah, we cannot use the Hamming distance because we don't have any binary data, right? Because the Hamming distance, remember, is just the number of differences in a string of characters, right? Or it is just the sum of a binary code. So we cannot use Hamming distance. What else are our options? Let's try correlation, the Pearson R distance. And it took only 2 iterations, but it is not good. That's what we got. Here's our answer key. Well, the 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 um the classification over here are all over the place, or the clustering is all over the place. So it's not a very good fit. But we know we should have expected that because we know that the grouping will be based on the actual distance between the points, and the usual distance is essentially the Euclidean distance, right? So that's a cue for you na, or for you that what you need to use is probably Euclidean or squared Euclidean distance. But I guess this doesn't have the Euclidean distance. It uses just the squared Euclidean distance. Let's try CT block instead. Okay, this is from the CT block distance. or the taxi cab distance, and then this is the answer key. I don't know if it gave a better, well, it seems to have given us the best results so far, right? Okay. So you can play again with this if you want to know all the refinements or all the personalization that you can do with the k-means algorithm. So all you need to do is to right click on the k-means command, select help, and open the help browser. And then you will see all the different options. So here you see I just copied this part of the code for this demo, right? And there's some other nice way of presenting the data. You can mimic this when you do the project, and the codes are also given here. So you can just copy paste it and then modify it accordingly for your data, right? So, and then at the last part, you see here all the options that you can pass on: region distance, correlation, the Hamming distance, and all the other arguments that you can play with. All right. So that's the k-means algorithm. So for today, the actual program is, or the actual agenda is for me to present three classification algorithms. So let's have a quick 2-minute break. I'll need to get the charger for my laptop, but we'll continue on. But I'll shift to my PDF annotator so we can write some notes about classification algorithms, and I'll talk about the naive Bayesian, the decision trees, and the KNN algorithm. All right. So hold on, guys. Let's pause for 2 minutes. Okay, so I hope you guys are back. So I'm deciding which one to talk about first because there are three algorithms. One is quite long, or the discussion or the description will be quite long, but the other two are just quick descriptions. So which one? Oh, I'll start probably with the longest one first. which is a naive Bayesian classification algorithm. But before that, maybe I should introduce what classification algorithms do, right? So classification algorithms are sort of supervised machine learning algorithms wherein you want to train the algorithm to predict to which class a query data or a query point will belong to, right? So in essence, you will feed to it a bunch of data, right? For instance, you will feed to it the matrix mesh that we are working with the Irish data. So 150 specimen with all the four measurements. And then you will also feed to it the species list because it's a supervised learning. So it should have the answer key, right? So for each of the data points that you have, it should have the corresponding classification for all of those data points. That's why it's supervised. We're training it with more information than unsupervised learning. And then the goal is that for it to predict the classification of a query point. So you will give it a query point. Say you will get another Irish flower. You will measure its sepal width, sepal length, petal width, and petal length. And then you will feed those data into the model. And then the model will predict whether it's virginica, versicolor, or setosa. All right. So that's basically the idea. Now, we'll consider three basic methods. Of course, there are more methods available, and there are more complicated methods available. But let's consider just the most popular three. Right. First one would be say the naive Bayesian uh, classification method or classification algorithm. And then probably you might be thinking this should be probabilistic in some sense because of the term Bayesian, and you will be right because everything here is hinged on computing a posterior probability. So you want to compute the probability that your object will belong to a certain class given some predictor. Or the predictor, basically you can think of it as the data that you have, right? So this is the information that you have, the data that you have about the object, right? Or about the specimen that you have. So you want to compute what is the probability that it will belong to a certain class given that it has these measurements, right? And then you will do this for all the possible class, and whichever class will get the highest probability, then that will be the conclusion of our Bayesian algorithm. Okay. Now, probably elementary statistics will tell us that this probability is equal to the probability. This is the Bayesian theorem. Probability that the predictor will happen given you are within the particular class times the probability that you get the class all over the probability of the predictor happening. So that's how you compute the probability or the score for the particular class. So the score for the class is the probability that your measurement will belong to a certain class given the set of predictors that you have. And this is posterior because you will do this after after the training is done. These probabilities are a priori, or uh, there are prior probability because we will compute them at the training stage. Okay. And then this is the likelihood that the predictor will occur given that you know that the particular object or the particular data belongs to the certain class. And we can compute this because we have the answer key, right? We have the species list. This is a train. This is a what? This is a this is a supervised learning algorithm, right? And then you will do this for all the possible class given your predictor, and then you will just get which class got the highest probability, and that will be the output of the algorithm, right? Maybe let's have a quick example. And I lifted this from one of the links in our website. So I found a nice website among the list that talks about an Bayesian algorithm. And their example is classifying emails into either a normal email or a spam, depending on the words that occurred in the email, right? So here's the data that they use to train the algorithm. So they noticed that in normal emails, okay, among the normal emails, the word dear occurred 8 times. And then the word friend occurred 5 times. The word lunch occurred 3 times. And the word money occurred 1 time. So there are 17 samples from the normal emails. And then for the spam emails, they found the word dear twice, the word friend once. There was no mention of a lunch, and money was mentioned 4 times. And there are a total of 7 data from the spam group. Okay. And first, you can compute the probability that the word occurred. So this is the word occurred given the class, right? So that means the probability that the word dear occurred given that you are in a normal email is given by 8 over 17, right? Because out of the normal emails are out of all the data that we have from normal emails, the word dear appeared in 8 of them. So the probability would be 8 over 17, and that's around 47%. And then you will do this for everything. The word friend occurred in 5 of the 17 emails, so that will be approximately 29%. Lunch occurred, so this is 3 over 17 or approximately 18%. And the word money occurred 1 out of 17, so that's about 6%. Okay. So basically, you can think of it as the predictor, probability predictor, because our predictor would be the words given the class. And this probability will come into this part of the formula, right? Because we are computing the probability that the email belonged to a certain class given that the predictor word occurred, right? Now let's see. Mhm. All right. And then we can also do that for spam. So the probability that the word dear occurred within the spam class is 2 over 7. And 2 over 7 is approximately 29%. And then the word friend, about 14%. Lunch has probability 0, and money has probability 57%. And that makes sense, right? Whenever there's a mention of money, most probably it's a spam email, right? Unless you have very rich friends or very generous benefactors, you get the word money in your email a lot, right? And then say, let's see what's the probability, though I don't have the number here. Mhm. Oh, yeah. One thing, some some texts do not compute the actual probability of the class, right? So this is the actual probability of the class, but they don't usually compute the score this way because again, the idea is to compute this guy for all of the classes. But whatever the class is, the denominator is the probability of the predictor happening a priori. So that means this is just a scaling constant. It doesn't depend on the class. So people usually ignore this factor, okay? And they simply compute the score. So this guy is not equal to this guy because I deleted the denominator, but you can say this is proportional to that guy, right? So the higher this guy is, the higher this probability, the posterior probability is, okay? So probably we can call it the score. just to make the computations easier, the score of a certain class is equal to the probability of the predictor given class times the probability of the class occurring. Now, what's the probability of the class? Well, what's the probability that you have a normal email? So we got 17 specimen out of a total of 24, right? 17 plus 7, a total of 24 emails analyzed. So you're going to get the 24 here. Sorry. Not 24, but 17 over 24. And that is approximately equal to what? Is that 0.79? Let me just, if you have your calculators with you, so that will be, yeah, that's 0.71 rather, 0.71%, 71%. And then, let's see, the probability that you have a spam email is 7 over 24. So that's about 29%. Good. All right. Now let's compute the scores, or let's have a quick example. So what if the email, the query email, so this is what we want to classify. What if it has the string dear friend? So here I'll just apply the fundamental counting principle. So there are two strings here that we are testing. So basically what we'll do is we'll get the product of each of the predictors occurring given the class. So there would be more factors over here times the probability of the class, right? So for instance here, the score that it is a normal email, right? This query email with a dear friend title is within a normal email, right? So we can compute this as the probability that dear, which is our predictor, occurred given that it is a normal email, times the probability that the word friend also occurred given it is a normal email, times the probability that we get a normal email, right? And then just harvest these numbers from our table above. So probability of dear given normal is 0.47. And then friend given normal, that's 0.29. And probability of a normal email is 71%. So the score that we'll give to it is 0.47 times 0.29 times 0.79. And I guess this is approximately 10%. Or sorry, 0.10. So that's the score that we will be giving to the normal group, right? 0.10. Now we will compare it with the score that we'll get from the spam group. Okay, so just compute the probability that dear will appear in a spam email times the probability that the word friend will appear given it's a spam email times the probability of getting a spam email, right? And again, going back from our table, this is 0.29% times 0.14%, sorry, 29% times 14% times 29%, and this will be approximately 0.01. Hopefully my calculations are right. Let me know if there is some of the arithmetics being wrong, all right? So that means normal wins, right? Because it has a higher score. So the output of our naive Bayesian algorithm will be, it is most probably a normal email, all right? So that's how the naive Bayesian algorithm works, at least for a discrete probability distribution. So if you have a continuous data, say your data is not a count or it's not a cardinal number, it could be, say, the height of persons to classify if that person is a volleyball or a basketball player. So your data would be heights, and heights are continuous data. So you will use you will use probability distributions, continuous probability distributions to take care of that, right? But it will be a long discussion if I'll go into continuous probabilities. So we'll just rely on, again, MATLAB to compute all those probabilities for us. So is that clear? Do you guys have any questions about the naive Bayesian method? Essentially, it's just computing conditional probabilities. But don't worry if you're not into probabilities. All of these things will happen at the back end. So you'll see that it's another one-liner, the command, and MATLAB will deliver what we want, or will deliver the classification for us. Okay. Okay, so that's the longest algorithm of the three. So I'm looking good with respect to time. So I'll move on to the second. It seems that you don't have any questions. The second one, or the second method, are decision tree. Now, decision trees, it's not computational in nature per se, but the idea of decision trees is to produce a sequence of rules that can be used to classify data, right? So the idea is to sort of create a flowchart. So create a flowchart that will aid users to decide to which classification a particular query point will belong to. So the idea is that it will split the sample into two or more homogeneous leaves based on the most significant predictor in the training set. So back at the back end, it does optimization of a cost function to see the most accurate cutoff for the predictor. And it works either for categorical data or for string data, and also for continuous data. So I forgot to lift the examples, but probably one good example, which I erased. Hopefully I can recover one of them. Hold on. One quick example of the result of a decision tree algorithm. Unfortunately, I deleted it. Let me go to my Facebook account, and I sent it to myself, but there you go. I forgot to copy paste it in my iPad, in this PDF file. But essentially, yes. One example is to determine what kind of animal do you have based on its characteristics. Is it a hawk, a penguin, a dolphin, or a bear? Your classifications are hawk, penguin, dolphin, and a bear. Okay. And then the idea is the data that you have is a set of tables. You have specimen among a specimen of animals, and the classifications or the data is a yes or no question. Does it have feathers? Can it fly? And does it have fins? So for each of the animals that you have in your data set, there are three questions: has feathers, can fly, or has fins? And then you will also supply to the decision tree algorithm the answer key, whether those specimens are hawk, penguin, dolphin, or bear. And then the decision tree algorithm will produce what the name implies, a decision tree that will help us decide uh, systematically whether the specimen that you have or the query point that you have is a hawk, a penguin, dolphin, or a bear, right? So you can have something like this. On the top, you could have the question, has feathers? That's the first question. And then there are two possible answers. It always splits it into two or more homogeneous types. But the choice of these questions is based on an optimization procedure. Okay. Now there are two possible answers, a yes or a no, right? If you answer yes, then you have a follow-up question. Can it fly? And then you have two possible answers again, true or false. And then if it's true, then it's a hawk. If it's false, it's a penguin. All right. And then on the other branch, If you answered no to the first question, the follow-up question is, has fins? Does it have fins? Then if yes, it's a dolphin. And if it's a no, it's a bear. Of course, this is a very simplistic example, right? Uh, but in decision trees, we don't input this the ordering of the questions. If your data is continuous, you will have a threshold, as we will see later, right? So the decision trees are actually the output of a MATLAB algorithm.
Okay.
Decide for us what's the optimum questions to ask and at what levels, right? Question? Right.
Hello?
Yes, Clarence, you have a question?
It's a good question.
Okay, great. So the last one, I told you this other two algorithms are quite easy to describe. Probably as easy as implementing them in MATLAB. Number three is the KNN algorithm. KNN algorithm. It stands for the K nearest neighbors. Okay. Now, what you need to do is to supply MATLAB with the value of K. So you give MATLAB or you give the algorithm the value of K. And then this works this way. So suppose I have a bunch of data. So say I have purple data over here. And then say I have red data over here. Okay. Because remember, it's a supervised algorithm. So essentially, the algorithm is privy to the information about the grouping, right? So it knows which are red and which are purple, right? So, and then you add a query point. Say my query point is the black one, right? I want to know if that black point belongs to the purple group or to the red group. Well, the KNN algorithm will do it this way. All right. So you will decide what's the value of K. Say we give K equals say 8. Not 8. I'll want to make it odd. So say K equals 9, for instance. So as the name implies, K nearest neighbor. So I'll be looking for the 9 nearest neighbors. So which do you think are the 9 nearest neighbors? Of course, this is near the black point. This is near the black point. 2, 3, 4, 5, 6. Then I need 3 more. Say, well, it depends on what distance you're talking about, right? So probably this one, and say this one. Say the 9 nearest neighbors to the black points are the highlighted ones in yellow, right? And the algorithm is very simple. Each of those majority wins. Each of those neighbors will have a vote, and you will see what their classification is. The classification with the most members among the 9 nearest neighbors will be the winner, will be the predicted classification for the group. So here, how many purple points do we have? We have 1, 2, and 3. 3 purple, and that means we have 6 red. So that means the algorithm will tell us that this is probably a red point. Okay, that's simple, right? Any questions about that? Good. It's very simple, right? You can make a toddler, even a toddler, understand how this is done, right? But again, you need to choose what distance is appropriate for your particular algorithm. Okay. Now let's see how this is implemented in MATLAB. So let me shift back. Oops. Well, stop sharing from my tablet. I'm gonna go to MATLAB again. Okay. So I'll restore MATLAB. I'll get rid of everything. Clear, close all, CLC. Okay, good. And then let's start with the Bayesian algorithm. This 14-liner code is the Bayesian algorithm. So again, you load the Fisher Irish data set. And then for some reasons, I chose to call the outputs of Fisher Irish, the measurement, the matrix mesh of data. I called it capital X. I don't know why I called it capital X then, but you can just replace all the X's here by mesh. That's fine. And then you need the answer key. You need to supply the answer key to the algorithm because it's a supervised learning algorithm. So you can run these two guys or these three lines. Okay, then you'll get the data on your workspace. And then the Bayesian algorithm is actually in line number 5. So you have fit C and B. That's the naive Bayesian algorithm. So this is fitting, classification, naive Bayesian, right? And the inputs for the naive Bayesian algorithm, first input would be your data set. Second input would be the answer key, right? The species list. And then some optional parameters are the distributions. Remember our measurements here? If you look back at the measurement matrix, we do have measurements, continuous measurements. These are measured in centimeters, right? So you have petal length, petal width, sepal width, measured in centimeters. So it's a continuous data. So this is quite different from the example, from the email example I've shown you before. We're just working with cardinal numbers. So here we have a continuous data. So we need to use a continuous distribution. So you can select what kind of distribution you want the model to be fitted on. So in this particular case, I selected the normal distribution. And then in line number 7, I declared 2 query points. So I'm thinking, all right, I have a certain Irish flower whose measurements are 5.8 centimeters, 2.8 centimeter, 5 centimeter, and 1.45. And I want MATLAB to classify it either versicolor, virginica, or setosa. And then I have another specimen of measurements, sorry, of measurements 3.8, 1.8, 0.5, and 10. And again, I want to classify them, right? Now, line number 5 simply trains the model. So it used naive Bayesian to create the model MDL, right? Now, if you want to use the model MDL to predict to which class X test will belong to, each of the rows of X test, to which variant they will belong to, you need the predict command. So predict, first input would be the model. We have already created the model MDL, which is trained using the naive Bayesian method with the data sets that we have, right? And then the second input to the predict command is the query points, okay? And then probably I can talk about line 16 to 34 probably on Tuesday. So that means we have changed of plans. I'll still meet you on Tuesday, probably just briefly continue the discussion of the codes, and then I'll give you I'll answer any questions you might have with the problem set. Okay. And then this guy is probably just a scatter plot just to see yeah how just to see where the query points and the training points are with respect to the classification. All right, so let me run the entire thing. I'll press F5 and we will see that there we go. So the query points are this is the training data. So the blue ones, the blue ones, the red ones, and the yellow ones are the setosa, versicolor, and virginica respectively. And our algorithm knows that, right? The challenge to the algorithm is to classify this data point. Actually, there are 2 data points. I don't know why I only graphed one of them. But basically, what's the prediction for the data points? Well, if I go to the command window, there are 2 answers here inside the class out structure. The first one is a versicolor, and the other one is the virginica. So the prediction using the Bayesian model is that the Irish that measured 5.8 by 2.8 by 5 by 1.45 is most probably a versicolor, and the one that measured 3.8 by 1.8 by 0.5 by 10 is a virginica. All right. And then I'll talk probably next time about the cross validation. So I'll probably need another 15 or 30 minutes just to talk about that, but we'll reserve that for Tuesday. Okay. So that's simply the naive Bayesian algorithm. Maybe let's take a peek at the decision tree algorithm. It's much shorter. Okay. Now here again, I load the Fisher-Irish data set. The measurement data is in matrix X. The species list is in matrix Y. And then, hold on, let me clear my workspace. Okay. The decision tree modeling is done in line number 5, so it's quite easy. So the syntax is fit T3, right? So you are fitting a classification algorithm using the decision tree algorithm. The inputs are just X and Y, your training data, and the species list. Okay. And then line number 7 and line number 8 will give us a graphical look at the decision tree. And then line number 10 will do the prediction. Again, we are using the predict command, which will use model 2, which is the model trained using the decision tree algorithm. And this guys are query point. Say I have an Irish Y0. Let me put 0.5 by 0.3 by 5 by 5. So those are my measurements. Okay. And then let's see, I'll press F5 and this is how I get. So this is the output. This is the decision tree. And again, here, I don't know if you can see it. Maybe I can magnify it. All right, just 200%. Then I can scroll. All right. So the top level will simply ask, I don't know if you can still see it. Here, here, the decision here is whether X3 is greater than 2.45. So the decision algorithm, the decision tree algorithm identified that's the first question to ask, whether X3 is less than 2.45. So that would be the measurement in the third column. So is it less than 2.45 or is it greater than or equal to 2.45? It's quite different, quite difficult, but let me make it smaller. Hopefully you can still see it. And then if it's less than, so if X3 is less than 2.45, then you can readily conclude it is a setosa, right? And then if X3 is greater than or equal to 2.45, then you go to the next decision point. Now, in this decision point, you have to decide or to check whether X4 is less than 1.75 or not. If it is less than, or if it is greater than or equal to 1.75, you will conclude it's a virginica. Okay. If not, then you will go to this decision point. So you will look again at X3, if X3 is less than 4.95 or the other way around. If it is not less than 4.95, it's a virginica. If it is less than 4.95, you go to the next decision tree. And at this juncture, we're checking if X4 is less than 1.65 or not. If it is, it's a versicolor. If it's not, then it's a virginica. So really, it's a flowchart for deciding what species or to which species your specimen will belong. All right. But of course, you don't need to do the classification manually. We use the predict command, and it says here that the specimen that I had, the 0.5 by 0.3 by 5 by 5, is a virginica. When one strong point of the decision tree algorithm is that it was able to decide it was able to determine that X3 and X4 are most probably the only things that matter in classifying the species of the Irish. Because in this decision tree, you won't see X1 and X2 being mentioned, right? And that's why I kept on using in the other algorithms X3 and X4, because it seems that those are the only two parameters or the two measurements that matter. Okay. Right. It's almost time. Only 2 minutes. So I'll reserve the KNN algorithm, the demo of the KNN algorithm, though it's a little bit long because I made some modifications to it. But let's do that on Tuesday, together with the short lecture on cross validation and how to use the MATLAB classification learner app. So it's a very powerful app that will allow you to run several algorithms all at once, and then you can choose which one is the best. And that built-in app can also produce cross validation, or will give us an idea of how accurate the classification was. All right. So that means again, change of plans. We'll still meet on Tuesday. All right. I wasn't able to finish everything today, but for sure, we'll be done on Tuesday. So you'll get the problem set on Monday. Then you can start working on it uh, starting Monday. And if you have questions, you can set a consultation with me. All right. So, any questions about the things we did today? All right. I'll take your silence as a no. So, okay. Thank you guys for joining me again for another 90 minutes of AMAT 255. Hopefully, the second to the last meeting. So, let's call it a day now and rest. So, you guys have a good night, and I'll see you again on Tuesday. Bye, everyone.
Thank you, sir. Thank you,